Hey there, everyone. Ready to dive into some stats with me today?
Always happy to talk stats.
Today, we're looking at expectation value variance and standard deviation.
Yeah, those are pretty fundamental concepts.
They sound a little intimidating, but
Uh-huh.
they help us understand how random variables behave.
And that's pretty much everything in the world, right?
Yeah, pretty much. So these concepts help us go beyond simple averages.
To get a better picture of the spread and variation within a set of data.
I like that, like looking under the hood.
Exactly.
So let's start with expectation value.
Okay.
I've also heard it called the mean, but what does that actually mean in this context?
So imagine you have some random process like rolling a die.
Okay. Yeah.
The expectation value, or the mean, is the average outcome you'd expect to see if you repeat that process over and over and over again.
Okay, I see.
Mathematically, it's a weighted average,
Okay.
where we're considering both the value of each possible outcome and its probability.
So it's not just like adding up all the outcomes and dividing by the number of outcomes.
It's not a simple average rate.
Right.
It takes into account how likely each outcome is.
I see.
So for example, with a fair six-sided die, each face has an equal probability of 16. To calculate the expectation value, we multiply each face value.
Okay.
So that's 1, 2, 3, 4, 5, and 6 by its probability, which is 16, and add all those results together.
So we're weighting each possible outcome
Yeah,
by how often we'd expect it to show up.
exactly. And if you do the math for a fair die, you get an expectation value of 3.5.
3.5.
Yeah, which of course you can't roll.
Right, you can't roll a 3.5. It's a weird die.
But it represents that central tendency.
Okay.
Like the long-term average as we keep rolling and rolling and rolling.
I see. Okay, so that makes sense.
Yeah.
But we know we don't always get a result right around 3.5 when we roll a die.
Nope.
Sometimes it's higher, sometimes it's lower. How do we account for that variability?
That is where variance comes in.
Okay.
Variance measures how spread out the data is.
Good.
How much individual results tend to deviate from that expectation value that we just calculated.
So a higher variance means the results are more scattered,
Yeah,
and a lower variance means they're more tightly clustered around the mean.
exactly.
Oh, yeah.
So to calculate the variance, we look at the difference between each possible outcome and the expectation value.
Okay.
For example, if you roll a 1, the deviation from the expectation value of 3.5 is managed 2.5.
Okay, I gotcha. And then we do that for every possible roll.
You do, yeah.
But wouldn't those differences sometimes be positive and sometimes be negative, which could cancel each other out?
Yeah, you're right. That's why we square each of those deviations. Squaring ensures that we're only considering the magnitude of the difference, right? Not whether it's above or below the mean.
Okay.
So in this case, we'd square minus 2.5 to get 6.25.
Okay.
Okay.
So we square each deviation from the expectation value.
Yes.
What's next?
So just like with the expectation value, we weight each squared deviation by its probability.
I see.
In the case of our die, that's still 16 for each side.
Right.
We add up all those weighted squared deviations, and that gives us the variance.
Okay, so variance is essentially a measure of how much, on average, the data points are spread out around the mean, taking into account how likely each data point is.
Got it.
It's like a numerical way to express the variability.
Exactly.
So for a standard six-sided die, what would the variance be?
If you go through all those calculations,
Yeah.
the variance for a six-sided die is approximately 2.92.
2.92.
Okay.
So that tells us the results of our die rolls tend to vary around the average of 3.5.
Right.
I have to admit, though, I'm having a bit of trouble visualizing what a variance of 2.92 actually means.
I understand that.
Is there a way to think about this in more concrete terms?
So you've hit on a key point. While variance provides a ton of information,
Yeah.
it's not always easy to interpret because it's expressed in squared units.
Okay, I see.
That's where standard deviation comes in.
Standard deviation. Okay, yeah, I've heard of that.
Yeah,
I think it has something to do with the square root of the variance, right?
you are exactly right.
Okay.
Standard deviation is simply the square root of the variance. So in our die example, the standard deviation would be the square root of 2.92, which is approximately 1.71.
Okay, so by taking the square root, we bring the measure of spread back into the original units of our data.
Exactly.
Oh.
So now we can say that the results of our die rolls typically vary by about 1.71 points around the average of 3.5.
It gives us a better sense of how much we can expect the rolls to differ from the mean.
It's a lot more intuitive.
Yeah, this is starting to make a lot more sense now.
Good.
So we've gone from understanding the average outcome with expectation value, to quantifying the spread with variance.
Yep.
And then finally to a measure of that spread in the same units as our data with standard deviation.
Mm-hmm.
It seems like all these concepts build on each other.
They do, they do. And while we've used this simple example of a die roll to illustrate these ideas, their applications extend far beyond games of chance.
Yeah, I bet.
Understanding expectation, variance, and standard deviation is really fundamental for analyzing and interpreting data in so many fields.
Yeah.
From finance and economics to scientific research.
You name it.
Even everyday decision-making.
That's fascinating. So we could apply these concepts in so many real-world scenarios.
Oh, tons.
But before we dive into those applications,
Yeah.
let's take a quick pause here to make sure we've got a good grasp on these foundational ideas.
Okay.
Okay, I think I'm ready to move on to some real-world applications.
All right, sounds good.
Where do we see these ideas of expectation value, variance, and standard deviation playing a role in everyday life?
Well, let's think about a situation where you're trying to decide between two investment options.
Okay.
Let's say you have two stocks, and they both have an average return of 8% over the last 5 years.
So based on their expectation value or mean return, they look pretty similar.
Right, they seem pretty similar. But that's where variance comes in.
Okay.
Let's say that one stock has a very low variance, meaning that its returns have consistently been around that 8% mark. But the second stock has a much higher variance.
Okay.
So its returns have been kind of all over the place. Some years significantly higher, others much lower.
So that second stock sounds a lot riskier, even though its average return is the same.
It is riskier, yeah.
It seems like there's a greater chance of ending up with a lower return, right, in any given year.
Exactly. So variance and its counterpart standard deviation help us quantify that risk.
Okay.
In this case, the stock with the higher variance and therefore the higher standard deviation represents a riskier investment.
I got it.
Even though they have the same average return.
So lower variance means less risk.
Generally, yeah.
And more predictability.
Exactly.
I bet this idea applies to way more than just stocks, right?
It does, absolutely. Think about like scientific research.
Okay, yeah.
Let's say you are testing the effectiveness of a new drug to lower blood pressure. So you give the drug to a group of patients, and then you give a placebo to another group.
Yeah, a classic controlled experiment.
Right.
Okay.
You'd measure the changes in blood pressure for both groups.
Right.
And while the average change in blood pressure could be similar between the groups, the variance could tell a very different story.
Oh, interesting. So even if the average effect looks good,
a
high variance in the drug group might mean that it has unpredictable effects on individuals.
Exactly. Like some people might see big drops in blood pressure, while others might see little or no change or even increases.
I see.
That higher variance could point to inconsistencies or side effects of the drug.
So variance can be kind of a red flag.
In a way, yeah.
It's telling us to look deeper.
Exactly. It tells us there might be more to the story than just that simple average.
Okay.
There might be other patterns or factors influencing the variability.
I'm starting to see that these concepts are like tools, like detective tools to help us unguard the information.
Yeah, exactly.
And look past those averages.
They help us ask better questions about the data and to really get a much better understanding of what is actually going on. For example, let's say you're comparing two different marketing campaigns.
Okay, yeah.
And one has a higher average click-through rate, but also a higher variance.
Oh, interesting. So on average, more people are clicking the ads in that first campaign.
Right.
But that higher variance means that some ads are doing really well, right?
Yeah.
But others are totally falling flat.
Exactly. And that is really valuable insight because it suggests that you can maybe refine your targeting or adjust your messaging and get better results.
So variance isn't necessarily a bad thing then.
It's not good or bad.
It's all about context.
Yeah.
And using it to make better decisions.
Exactly. It helps you understand the bigger picture.
I like it. Okay, so this is really making me think about data differently.
Good.
Are there any situations where we should be really careful when we're interpreting these concepts?
That's a great question. One common pitfall is assuming that a high average automatically means something positive.
Right.
Or that a low average automatically means something negative.
Okay, yeah.
It's really important to consider the variance alongside the average to get the full picture.
So like if a company's bragging about a really high average customer satisfaction rating.
Yeah.
What if the variance is super high?
Right, exactly. It could mean that a few really, really happy customers are skewing that average,
I see.
while a much larger number of customers are having terrible experiences.
Okay, so that average alone can be misleading.
It can, yeah.
So never trust an average without looking at the variance too.
Exactly. Are there other things we should keep in mind?
Oh yeah, are there?
Another important point is that these concepts work best when the data follows a normal distribution.
What is that?
It's that familiar bell-shaped curve.
Oh, the bell curve. Yeah, I've heard of that. That seems to pop up everywhere.
It does. It does.
But not all data has that nice shape, right?
Exactly. If the data is skewed,
Mm-hmm.
if it's lopsided in one direction,
Yeah.
or if there are outliers,
Mm-hmm.
which are extreme data points that are far from the rest of the data,
Yeah,
then things get a little bit more complicated.
I see.
In those cases, the mean might not be the best way to measure the center,
Okay.
and the variance and standard deviation might not give us the whole picture about the spread.
So
Yeah.
these tools are really powerful, but we need to know their limitations.
Right.
And when they're not appropriate,
Yeah.
it's all about picking the right tool for the data.
That's a crucial point.
Okay, got it. This has been so insightful. It feels like we've just scratched the surface, though.
I know,
There's so much to explore.
But we've laid a good foundation.
Yeah.
And there's really so many applications for these concepts.
Maybe we could do another deep dive sometime.
I love that.
Okay, cool.
But for now,
Yeah.
let's wrap up our exploration of these foundational statistical ideas.
Okay, so we've learned expectation value, variance, and standard deviation. And they're powerful tools for understanding data.
Yeah.
It's not just about plugging numbers into a formula, is it?
It's not.
We need to think about what the numbers actually mean.
Exactly. It's not just calculating the statistics.
Right.
It's about understanding what they mean.
Like how a high average isn't always good and a low average isn't always bad.
Exactly.
We have to look at the variance
That's
too
right. Yeah.
to get the whole picture.
And we have to think about the data itself if it doesn't fit that bell curve shape.
The normal distribution.
Right? The normal distribution, we might need different tools to analyze it.
It seems like it all comes down to picking the right statistical tool for the job
It does.
and knowing the limitations and really thinking about the results,
Exactly.
not just blindly trusting the numbers.
And I think that shows how cool statistics is.
Yeah.
It's not just about the math. It's about using the numbers to tell a story,
Right.
to find the patterns,
Uh-huh.
and to make better decisions.
I like that. It's a whole new way of looking at the world,
It is.
to see the variations
Mm-hmm.
and to understand what it all means.
So the next time you see some data,
Yeah.
whether it's in a news article
Oh, yeah.
or a financial report,
Yeah.
or even just your own observations,
Uh-huh.
don't just look at the average.
Okay.
Ask about the spread, too.
Yeah.
Think about the variance. Maybe even try calculating the standard deviation.
I'm ready to put on my detective hat and get to work.
That's the spirit.
Thanks for walking us through this today. It's been really cool.
It was my pleasure. Remember that understanding these concepts, it can help you make better decisions,
Right.
assess risk more accurately,
Yeah.
and really understand the world around us.
Thanks for listening, everyone.
See you next time.